I remember quite a long time ago, it seems like, sometime in the early 1960s, when our solar system looked like this, according to Rand McNally. And some of the things that couldn't believe, where you looked on top, you see they have the dwarf planet Ceres, which looks like a kind of an elongated or kind of a fat pancake. Uh, Nothing is to scale. Um, Possibly the only thing that is close would be the comparison between the Earth and Jupiter. But to make things more official, um, uh, Tina, can you admit Charlie? Thank you. So to make things more official, they decided that Ronald McDonald needed to get into the fray, and that way these things are more official, since we have Ronald McDonald standing on each of the planets, and we're learning about the planets that way. Of course, this is a little bit better than the the solar system that we had in the 1930s with Buck Rogers. Uh, it's certainly, I mean, I'm not quite sure what a pterodactyl is doing up there, but it certainly is something more than we had before as far as solar systems are concerned. But so things have definitely improved over the last 30 years, between 1930 and 1960. In 1990, this is what our solar system looks like again. And again, there's not much in the way of planets that are to scale. It does show the Kuiper belt. It does show the trans-Neptunian asteroids. But other than that, there's still, no very little difference between this and the Ronald McDonald solar system. Yet another way of looking at our solar system is simply looking at the facts. And you can see that you can start using your imagination on this and then wonder, well, gee, the length of the year on Mercury is 88 days. And then you start to realize that there is a problem with saying days. Are you talking about days, length of the year on Mercury? Are you talking about Mercury days? Are you talking about Earth days? And there's not a whole lot of differentiation between all this. Possibly the thing that'll attract your attention most is the surface temperature, because that's actually given in Fahrenheit, and it does have some meaning to us. For instance, the Mercury surface temperature range is more than 1,000 degrees, almost as bad as Iowa. So certainly just having something like this does get your imagination going a little bit. But of course, we go back to the other way of showing our solar system, and that's by using tutorials like this, which again are just totally out of scale. I never knew that the Earth was actually a little larger than the sun. The other thing is that this doesn't really show the actual movement of the planets. They do not stand in one place and go in circles around our sun. They are actually moving objects that are dragged across space by the gravity of our sun. And our whole solar system is actually moving toward, actually moving around our galaxy. And as it does that, it's actually moving perpendicular to the movement around our galaxy. So one trip around our galaxy takes about 230 million years. So we haven't gone around that much since the formation of our solar system. And to tell you the truth, we don't go straight around. We actually go up and down with kind of like a carousel. One of the horses on the carousel, where it actually goes up and down as it moves around our galaxy. Now, one of the things that is kind of fun to think about is, how did it all start? And to do that, we need to go back to the beginning, at least what's considered to be the beginning of time. And that would be the Big Bang. And we have the plasma that came out of that, uh, the materials, and as they actually coalesced, they formed clouds of hydrogen. And these clouds of hydrogen basically coalesced around pockets of gravity. So you have a cloud of hydrogen, and as gravity pulls it in, the temperature within that cloud begins to climb. And as the cloud condenses and the temperature rises, reactions begin within that cloud. Now keep in mind that at this point, the cloud is only hydrogen, since that's pretty much what came out of that Big Bang. So as the temperature reaches millions of degrees, there is a reaction that takes place. Now, this reaction, well, we're calling it fusion, but really there's a history behind this. The first thermonuclear explosion was actually an accident, when over 705,000 students squeezed themselves into a phone booth. The secret sauce from George the Chili King probably added another 3 megatons to this thing. And unfortunately, the entire campus was destroyed by this thermonuclear bomb. Now, they didn't quite realize what was going on at that time. They actually had to take a step back and figure this out. Now we know that in order to have a thermonuclear explosion, we have to have like particles actually come together. Now, when you have two particles that have the same charge, they repel each other. But in order to have this thermonuclear reaction, they had to somehow come together. And the only way you can do that is to take these particles, these protons, the nucleus of the atom, and you had to heat them. Not quite sure if that's the way you do it, but the idea is that you increase the energy of these this nuclear material, and you gain the energy, you increase the energy so much that they actually overcome their like charges and will combine to form a heavier element. So here we have hydrogen elements coming together to form helium. So within this first cloud, we have hydrogen condensing into a very, very hot spot where nuclear reactions take place and a star is born. The star actually blows off the gases that surround it and becomes a star, well, in this case, it would be a very high energy star since there's so much mass in this star. So within this star, there are hydrogen nuclei changing into helium nuclei. And it does that, giving off a great deal of energy and enough energy to sustain itself. So again, we have two hydrogen particles come together. It produces 3.5 million electron volts of energy. It sounds like a lot. To tell you the truth, a gnat burp is probably millions of times more powerful than 3.5 million electron volts. What makes the energy so much within the star is the fact that there's hundreds of billions of nuclei all coming together and reacting and becoming helium. So within the star, within this gas that is now turning into the star, we have gravity pushing everything together. And then we have the reaction of the nuclear fusion pushing everything apart. This is known as hydrostatic equilibrium. It's where everything is equal, it's in balance. And these are called main sequence stars. These are normal stars, much like our sun, that will probably remain stable for several billion years. So we have the star merrily changing millions of tons of hydrogen into slightly less millions of tons of helium and giving off a tremendous amount of energy. It doesn't always last like that. There is a kind of a turning point because the star can't get rid of the helium. The helium is a waste product. So the helium actually ends up in the middle of the star, in the center of the star, and it builds. And as it builds, temperatures and pressures increase. And as they do, the star leaves what's known as the main sequence. It is becoming an unstable star, and it'll actually begin to expand. And as it expands, not only does it get larger, it gets actually, it gives off more energy, and we have the ever-expanding shell of helium now growing within this star. At some point, the temperatures and pressures will be high enough to actually make the helium fuse into heavier elements. The helium will actually fuse into the next fissionable element, which is carbon. So we have within the star elements being formed first of all, out of hydrogen, then becoming helium, and now becoming carbon. The star expands. And as it does that, the temperatures and pressures will increase. And within that star, new elements are being created. This is known as nucleosynthesis, where particles will come together, combine, give off energy, and become heavier elements. So within the star, we have ever-expanding cores of helium, carbon, oxygen, and as more and more elements are formed, the star will actually form new and ever-increasing layers of heavier elements. It doesn't go on forever. In fact, the heaviest element that will be formed within a star will be iron. And that's number 26 out of 92, actually. So we have an awful lot of elements to make within the star, which doesn't happen that way. So when the star begins to, well, manufacture or create iron, it's no longer creating more energy. In order to have the iron fuse into heavier elements, it'll take more energy than that star is capable of creating. This is also known as the onion skin star because it kind of looks like an onion skin. I've always said that astronomers really don't have a tremendous imagination. They call things as they see them. So we have the onion skin star, and in the middle we have iron. And if you take a look at the chart on the bottom, you can see that the hydrogen burning will last a couple of billion years, and each element will take less and less years, less and less time, I should say, until you get silicon burning into iron. And that'll happen over 5 days. When iron is in sufficient quantities in the center of that star, the star will explode. This will become a supernova. And when it does that, it doesn't take days. It doesn't even take hours. It'll take seconds. The star will implode and then send a shock wave out beyond the star. And that's what we're reading when we're looking at these gravity waves, because the star will actually jump out at tremendous speeds. And when it does that, we have an expanding cloud of gases. And within those gases, we have a lot more than hydrogen. We have actually the explosion itself will release enough energy to be able to, well, form the rest of the periodic table. So we have now a cloud of a lot of mass, a lot of different elements, now all coming together. And once again, the heat, the energy from gravitational contraction will actually form not only the star, but will form planets as well. These pockets of matter will coalesce into planets, asteroids, comets, and an awful lot of dust. The first planets that were formed were probably Jupiter and Saturn. And they formed, well, they started out beyond the frost line and then came back. The reason is because not everything on Jupiter and Saturn is frozen solid. Uranus and Neptune are pretty much solid, but Jupiter and Saturn, Jupiter mainly, actually pulled a lot of the mass out of Saturn and also pulled mass out of the inner planets as well. So we have a frost line where everything beyond that line will be solid ice and not necessarily water ice. It'll probably be other types of ice as well. So if you're close enough to our star. If you're within the frost line, you might actually be within the line that we call within a zone called, we call the habitable zone. Now, the habitable zone is made up by astronomers as a place where you have liquid water. Now, of course, if you're beyond the frost line, everything is frozen, and that doesn't work. So we have the habitable zone where we have liquid water, where it's possible to have that. If it's too close, the water is just boiled away. If it's too far away, then everything is frozen. And if it's just right in the habitable zone, then it's just right. And now you understand why this is called the Goldilocks zone, because it's just right. The other thing which scientists look at, astronomers look at, is the size of the planet within the habitable zone. If it's too large, then the gravity will be too strong, and the atmosphere will be too dense. If it's not big enough, then the gravity will be the other way, where it won't be the atmosphere won't be dense enough to actually hold itself to the surface of the planet. So we have our solar system. Blue is where that's the Earth orbit. Red is the Mars orbit. Yellow is the Venus orbit. And then you have the sun in the middle. This is not to scale. So we have our habitable zone right over there. And as you can see, Venus at one point was well within the habitable zone. But over time, our sun has actually increased in energy. And as our sun increases in energy, the habitable zone will actually move out. So with the increase of energy of our sun, our habitable zone has moved out, so that now Venus is too close to the sun, much too hot. There is no water on Venus. As you can see, the Earth is well within the habitable zone. Glad to see that. But it's interesting because Mars is also within that habitable zone. So within that habitable zone, we'll have our Earth. They have found more than 50 solar systems that have temperature, that actually have planets that will, within the habitable zone, that could support liquid water. Now, why is water so important? Well, actually, yes, we need it to drink, but the main thing is the fact that the properties of water also include a universal solvent for life chemicals. They need to have a place to dissolve and to react into materials that will form life. When our solar system formed, the heavier particles, the more dense particles, were actually pulled in closer to the sun. It's just like if you have something heavy, and it'll actually move toward the center of things. The colder outside disk has mainly icy particles and gas. The inner part of our solar system has rocky particles and ice and silicates and iron. So we have the life-giving chemicals within the inner part of our solar system. So taking a look at our solar system, as you can see, We have inner rocky planets and outer gas giants. We actually, and plus we have some asteroid belts. So you can see that our solar system is actually made up of two parts. We have the inner planets and the outer planets. So if we were to kind of take a look at our solar system and move out and take a look at the planets, we would see something like this. So from Earth's orbit, we have the inner planets, we go across the asteroid belt, and then we have Pluto's orbit, and then go down into the Kuiper belt, and then we have Sedna. Where the heck did Sedna come from? And the Oort cloud. Where did that come from? Is that part of our solar system? Well, okay, so we have the inner solar system, which has the 4 rocky planets. We have the asteroid belt, and then Jupiter, part of that. That's, if we condense that down to the middle, we have the outer planets, and you can see the way Pluto will actually dip inside the orbit of Neptune. And then we have Sedna. What's a Sedna? I wonder if the song is wrong. I wonder if the song should say, "My very educational mother just served us 9 puny strawberries." Well, that might be interesting. Anyway, but taking a look at our solar system, it does consist an awful lot more than just our planets. We have the terrestrial planets, and then beyond that, we have the Jovian or the giant planets. And then beyond that, beyond the Kuiper belt, we have the trans-Neptunian objects. And it's part of these objects that we might actually find Planet 9. And those solar systems, we have the inner, outer, and the Neptunian planets, are all a tiny spot in the middle of a cloud of dust and gases and ice, which is called the Oort cloud. And as you can see, the Oort cloud could be 100,000 astronomical units wide. Now, 63,000 astronomical units is equal to a light year. A light year is 6 trillion miles, give or take a foot or two. So what is this Oort cloud? I mean, it's just this cloud of dust and gases and ice, all held in by the sun's gravity. Possibly a better way to think about this is the fact that when our gas cloud condensed and became our solar system, what was left was this cloud of dust and dirt and ices, and you can kind of think of it as a bathtub ring. So when you release the water and all goes down the drain, the center of gravity, I guess you can call it, what's left is this ring of mass that's kind of left over from the creation of our solar system. So we have our bathtub, and then we let the water out, and the only thing left is our bathtub ring. What we call the Oort cloud. So have we ever seen anything from this cloud? Well, Believe it or not, we have. And the one who saw it was most likely Dr. Daniel Morehouse, president of Drake University in 1908. He was working on his doctorate, and he was working with the telescopes in Chicago, and he happened to find a comet. And based upon the orbit of this comet, he deduced that it probably came from the Oort cloud because it was way beyond anything that had ever been discovered before. So part of our solar system are also comets. And we have comets that come from the Oort cloud and comets that come from a little bit closer. Comets are kind of fun. First of all, they're not very solid. Their tails always move away from the sun. And most of the comets we see are called periodical comets. In other words, they are actually in orbit around our sun and will make periodical appearances given time. And we have lots of those. And they will sprout very long tails that are formed by the by the solar wind that pushes away the material that's part of the head of the comet. And what it's actually pushing away is some of the outgassing that the comet actually does. So we discovered what makes a comet when we had one of our probes actually catch up to one. This was Comet Tempel 1. And we decided that we wanted to take a look inside this comet. Now we know that comets are not really solid objects. They are actually let's say a conglomeration of materials that are kind of held together by gravity. So the idea is that if we took something and we pushed it into a comet, we should, basically blast up a lot of material, and then we could analyze this material and be able to tell what a comet is made out of. So we decided to do that with Tempel 1, and so we blasted a what was an 800-pound copper impactor at 23,000 miles per hour. It hit the comet, partially vaporized, and it actually pushed so much material into space that we couldn't take pictures of it because there was just too much of it. We actually had to wait until we actually got another probe to take pictures of Comet Tempel 1. But we found that comets are actually fairly nebulous things that outpour a lot of gases and materials as they go around the sun. And for the longest time, it was thought that comets were the main source of water on the Earth, that the water on the Earth came from beyond. Very recently, in the last year, they started taking a look at certain types of meteorites. They're investigating new planetary disks. And what they're finding out is the fact that water may actually be the most common molecule in the universe. When planets are being formed, the planetary disk that the star comes from is actually filled with water. Not necessarily liquid water, but certainly gases and hydrogen that will eventually make water. So these materials will form rocks. These are called enstatites, chondrites, which is a form of meteor. Actually, it's the material that our Earth coalesced from. So it's entirely possible that our Earth, since it pulled in so much of this material, these chondrites, that our Earth possibly started off wet. This is a new theory. And again, trying to figure out where the water came from. So as our planet was being formed, there's the chondrite. And again, a lot of the makeup of that particular rock is hydrogen. And hydrogen will form water. So as our planet was forming, it pulled in a lot of this interplanetary dust and materials, and from this material came water. Now, one thing that our planet has, that every other planet has, is dust. We got lots of dust. And this dust is actually helping astronomers find other solar systems. And this dust is everywhere. Comes from basically meteors and asteroids hitting each other. It comes from gases that will cool and coalesce into these rocks, these chondrites. So all this dust is out there, and we are covered with it. In fact, on any given day, the Earth will receive somewhere between 40 to 100 tons of this dust coming down from space. So if you really want to know why your windowsills are so dusty, there's the reason. Anyway, so as we orbit our sun, there's more dust, the asteroid belt. So as we orbit the sun, the planet will actually go through the dusty solar system and will actually pick up this dust. Given time, the dust will actually reform, will fill in the blanks after the Earth has passed. This is actually one of the definitions that was given to a planet, the fact that it actually cleans up after itself. Well, yeah, it may clean up after itself, but it only gets dirty again. Anyway, but the discovery of all this dust has helped astronomers find other solar systems. In looking at our own solar system, what we'll see is a lot of dust, which is a little bit warmer than its surrounding area. And you can see where the Earth has kind of cleaned up its area as it orbits the sun. So if we're looking at our solar system from well beyond our solar system, this is what our dust would look like. This is what our solar system would look like in infrared. Looking at other solar systems in infrared, for instance, Vega, you can see that there is a fairly extensive debris field around Vega, And so Vega probably has planets going around it. We haven't found them yet, but the assumption is there. So we find that Vega's planetary system is probably a good deal larger than ours. But then again, Vega is a much larger star. Looking at Fomalhaut at different frequencies, you can see that in infrared and ultraviolet, there's definitely the star, and there is a whole cloud of dust going around it. And taking a closer look at this particular object in the sky, Fomalhaut, you can see that this star has a ring of dust around it, and a closer look actually imaged a planet. This is the first time a planet was directly imaged through a telescope. So that's a pretty major thing, and you can see that in the 8 years that it was tracked, it moved that much between 2004 and 2012. Another debris disk that was looked at very carefully was HR 8799. I'm sorry it doesn't have a nice name to it, but the Spitzer Space Telescope, which is an infrared telescope, found a dust field that was huge. It was well larger than our solar system. You can see the size of Pluto's orbit in the middle of all that. So they imaged this particular solar system, and what they found was the fact that there are planets within this dust field, and a much larger solar system than our solar system. And in using computer enhancement, they were able to find 4 planets actually in orbit around the sun, their sun. You can see that their star has been blocked out so it doesn't overpower everything else. But given the computer enhancements, you can see that there are planets going around it. Actually, there's one more planet that's actually very close to that star, but it's been kind of covered up by the thing that's actually covering the star as well. So the orbits of those planets have been calculated. In fact, they even took a time-lapse movie of that particular star system. And again, this is the second time that planets were directly imaged through a telescope. And as you can see, it took 7 years in order to make this particular, well, not even 10 seconds long. Well, there's lots of other stuff in our solar system. One of those things actually fell to the Earth on February 15th, 2013. It fell in Chelyabinsk in the Ukraine, and it was well documented. It was actually the brightness of 30 suns. It just overpowered everything, and the boom, the sonic boom, the pressure wave that came from that object, which was about the size of a bus, was enough to blast out windows and knock doors off their hinges. So that's a pretty major thing. I mean, that's again about the size of a bus, and the pressure wave. It caused about 1,500 uh, injuries, uh, probably millions of rubles of destruction. And again, this was a pressure wave that just it exploded in the sky, and the pressure just knocked down doors and broke windows. So we get hit by these things. Again, we pull in somewhere between 40 and 100 tons of material a day, and sometimes something bigger will go through our atmosphere. And when it does, and we happen to find it, those things have been very well analyzed. And what we find is the fact that these asteroids, these meteorites that do make it all the way to Earth, will, in some cases, contain uh, organic chemicals in them. They will have water in them. They will have ammonia, methane, some other hydrogen-based and carbon-based elements. And so it's possible, if you think about it, that maybe life may have begun someplace else and hit the Earth some millions or billions of years ago. But they've also found that these organic chemicals have been found on other bodies as well. For instance, Ceres, one of the dwarf planets, they found lots of organic materials on this world. They found amino acids on it. And so they found also the possibility of life on this body. Maybe it's on the inside, but certainly isn't on the outside where radiation and other things will get to it. But there are biologically active elements that have been found on this dwarf planet. Which brings up the question, is our solar system like other solar systems? Do other solar systems have the things that we have? But we also have the Earth, and the Earth, as far as we know, has intelligent life on it. So is our solar system so unique that it has the Earth, or is it just another solar system like the 2,000 or 3,000 that we studied through the Kepler investigation probe? So we can take a look at some of the other solar systems and compare them to our solar system to see if there are similarities and exactly what the differences are. I'm going to be using solar systems where the planets are well established in their habitable zone. And obviously the habitable zones are based upon the energy output of each of their stars. So one of the habitable zones that we're going to look at is Kepler-90. And you can see that if we compare planetary sizes, you can see that, well, it runs the gamut from small to large, although the smallest planet is about the size of our Earth or a little larger. Their largest planet is about the same size as our Jupiter. What makes this planetary system fairly unique is the fact that if you actually get the planets spacing from their sun in perspective, they are all about that far away from their sun. So the furthest planet at Kepler-90 is about the same distance as our Earth. So all the planets that are around the Kepler-90 system are fairly close to their star. Kepler-62, you can see that the habitable zone is a little smaller than ours. The star that is at the center of Kepler-62 is actually a red dwarf star, which has uh, planets going around it, yet all those planets are well within, again, the orbit of the Earth. And they are the planets themselves, with the exception of 62C, are all larger than our inner planets. Kepler-47, this is an interesting one because Kepler-47C, its orbit is elliptical. So there are times when it's closer to their star than at other times. Now, the Earth is the same way, but the differences aren't that much. It's only about 2 million miles. Kepler-47 is a good deal more than that. And as you can see, Kepler-47c is much larger than our Earth. In fact, it's about the size of Uranus. The latest one, well, Kepler-186 is one of the planetary systems that they feel has the best chance of life. And as you can see, Kepler-186f is well within its habitable zone. The orbit of that planet is somewhat circular. So it would be logical to think that there would not only be liquid water, but maybe some type of life as well around that planet. And one of the latest ones to look at that we've discovered is TRAPPIST-1. And you can see it has all sorts of planets. It has 7 planets, all going around a red dwarf star. But what makes this so interesting is the fact that all those planets, even though they're the same size, many of them are the same size as the Earth, all of those planets would actually be orbiting their star within the planet Mercury. So it's an interesting thing there. So our solar system again has what we understand our solar system to be, has the rocky planets and the gas giants. In addition, it has 2 belts, the asteroid belt and the Kuiper belt, plus it has the trans-Neptunian planets. But how does it compare to the other solar systems? If you're looking at planet masses and densities, the gas giants in our solar system are pretty typical. The terrestrial planets are on the low side for mass. So it's very difficult to detect low mass planets around distant solar systems. So maybe that's not really a good thing to compare to. The age of the solar system, we're about in the middle. Half are older, half are younger. The orbital locations of the planets, our solar system is lacking the planets that are orbiting close to their star. All of our planets are at a distance that is larger than the mean distance observed in the exoplanetary systems. So that's kind of weird. Our planets are more spaced out. The eccentricities of the other planets are more than ours. Our planets are fairly circular. Other other planets, other planetary systems do have fairly elliptical orbits, which means that their climates might be a lot more, well, there would be well, that wouldn't be nearly as stable as our climates. Finally, we have super Earths. And in our solar system, we don't have any. Just that simple. Yet super Earths are fairly common in other solar systems. So that's something that's pretty strange. We do know one thing, though, that at some time in the future, our star will will run out of fuel, it will swell, and will probably knock all the life off the Earth. As you can see right now, we are about 4.5 billion years into our life cycle, and in about 4.5 more billion years, it will expand. And when it does, in sometime in the future, it'll very easily take out the inner planets, and as the expansion continues, it will most likely take out Jupiter as well. So that's not a good thing to look forward to. But again, we're talking about somewhere in the vicinity of about 5 billion years from now. So at that point, our habitable zone will actually extend into or right around the orbit of Jupiter and Saturn. Does that mean that Jupiter and Saturn will have life going around it? That'd be interesting. Actually, what will most likely happen, since Jupiter and Saturn have elements that are gaseous and metallic because of the cold, those planets might actually dissipate. The gases will boil away as the heat from the expanded sun heats up that planet. Then our star will blow off its outer layers, will become a ring of gases, and the middle of that gas cloud is a tiny star about the size of the Earth. That little star has about the same mass as our sun, maybe just a tad less, but it's giving off a lot of energy. And it's giving off the energy in X-ray. These are other, what they call planetary nebulas. And these are the result of stars that are similar to our sun that have lived out their lives. So we have our white dwarf star that used to be our sun. It's about the same size, maybe a little bit smaller than the Earth, but it's giving off a lot of X-rays. A star similar to this happens to be a star that's orbiting Sirius. Sirius B is a white dwarf star. It's giving off a lot of X-ray, and as you can see, when we take a look at the X-ray image of that star, you can see that in terms of X-ray, it's a lot brighter than Sirius A. When it becomes a white dwarf star, it will slowly dissipate its energy and will turn dark. If we survived the expansion of that star, which I doubt, we would still be orbiting it. But there wouldn't be any energy coming from that star. And that'll happen in about 5 billion years. But don't worry about it, because in less than 4 billion years, our galaxy will be colliding with another galaxy called M31, the Andromeda Galaxy. And that will do more destruction to our solar system than the demise of our star. So either way, we're not going to be too much around. Next week, we're going to be taking a vacation at some of the hottest resorts in the solar system, Mercury and Venus.